Okay, so we've got 13 people so far. I think we're going to get many more. So, right, so we'll perhaps make a start on this tutorial. And the first thing I'll do is just remember to resume the recordings. Right.
Recording in progress.
Okay, so hello everyone. This is our tutorial on Fourier transforms, and so I need you to have access to tutorial 7 on the Canvas page so you can see the questions, and we'll go through some of the solutions, and I shall upload the solutions as well to this tutorial very shortly. Right, so can you all see my tablet? Yeah. Okay. Also, sorry to sound like a broken record, but could you please put your cameras on so I don't feel it says, and at that moment it's just me and one other. So if you put your camera on, that'll be great. So I can just gives me an idea of, like, yeah, if you I can tell by your face if you understand something or not. Makes you feel less lonely as well. Right. Great. Thank you very much. So, so we're looking at this tutorial sheet, and obviously parts of a lot of it just requires looking up functions from the table, applying the first and second shift theorem, and there are also some questions that do require a bit of integration for functions where we just don't have a choice. So I'm going to do one of those, not both, and then perhaps time through to duality. I don't think we need to spend so much time on that now, since we spent an hour this morning on that. And the little question at the end with an LR circuit. So, okay, so we'll start from the beginning, and let's just write this question down. So I'm just going to do some selected questions. If you have any questions, of course, please do use the chat, either publicly or privately, and I'll answer those when I see them come in. So question 1, part A. Function is 5 times a step function times e to the minus 2t. Okay, so that's a very straightforward one. We can just use the table of Fourier transforms just to find that directly. So if you get your notes up and go to that table, you will see that on the top row we have this. So let's just change the color here. So in the table, we have got that Fourier transform of a u of t e to the minus alpha t is equal to a over alpha plus j omega. So we add that from a table. So in our case, it's very simply just substituting the values in. So here we can see that a equals 5 and alpha equals 2. So in that case, the Fourier transform will be 5 over 2 plus j omega. Okay, so next one. So we've got a rectangular pulse this time in 2 pieces. Okay, so again, the table. see that the Fourier transform of a general rectangular pulse between t equals minus alpha and alpha is given by, from the table, would be 2 sine omega alpha over omega. So of course, in this case, alpha is equal to 2 in this case. And also what we're finding, so a Fourier transform will be this. So Fourier transform of this is the same as 4 times the Fourier transform of the rectangular pulse that's in the table. So in that case, it would be 4 times 2 sine 2 omega over omega, or 8 sine 2 omega over omega. Right, so while you write that down, just notice a question has come in. So in the exam, would we need to show the full working out for this type of question? No, it's just using the table, and just use the table. You can, what you would write is just say, from the table, this equals this, therefore the answer is that. That's the level we want. Okay. So you haven't got to go quite to the level I've gone, but just say from the table, this equals this, therefore the answer is f of omega. So yeah, so don't worry about that too much. Okay, and let's just do the last question, part C. So part C, obviously, now let's just write the question down first, but we've got the sum of 2 delta functions. Okay, so in this question, we need to find the Fourier transform of these 2 separate delta functions. So we can take the 2 outside. Okay, and then let's go to the table. So if you look at the table, you'll see that the Fourier transform of a shifted delta function, so let's just write this down, is equal to e to the minus j omega a. Okay, so in the first one, a equals 1. So if we look at this one here, we've got a equals 1, and obviously in the other shifted function, a equals minus 1. So therefore, our Fourier transform would be 2 times e to the minus j omega plus 2e to the plus j omega. Right. Now, obviously, you probably recognise this expression, so this will be fine as a final answer, but also you'll notice that it's also the same as 2 times cos of omega. Okay, and that's because of Euler's expression, which I wrote this morning, but as a reminder, okay. Actually, that's wrong. It's 4 cos omega, shouldn't it? Just realised. Okay, so the question, as everyone can see here, will we get full marks for using the integral definition, so using the table and vice versa? I think you'll get the same number of marks. Obviously, you would only use the integral definition if the question specified it, because want to avoid any confusion. So if it says find the Fourier transform, you use the quickest method to find it, basically, which will be the table. But if the question said prove that the Fourier transform of a function is equal to something, then the proof means that there's going to be a mathematical derivation. So that would be an integral. Okay, so if it doesn't say prove, then it would just mean just use the table. Also, the number of marks would be indicative as well of the method you need. So obviously, using the table, you would not get, there would be less marks, because obviously it's quite straightforward to use the table, whereas integrating would require more marks because there's more effort involved. Okay, so hopefully when you see the exam paper, it will be pretty clear what method you have to use. But if you want to play safe, use integral, of course. I'm only interested in the final answer, so as long as that's correct, that's all that matters. Right. Now, question 2, I want to leave, and I'll let you look at the solution, because it's a very long-winded integral. So it's actually one of the questions we're talking about now. It says calculate the Fourier transform of u of t times e to minus t times cos t. So there's a clue there. Calculate the Fourier transform. That obviously means there's going to be some mathematics. So that's not the same as finding. So that would be a proof. So I think I'll upload the solutions to that one, and you can go out through that one yourself, because it's straightforward but long-winded. Let's have a look at number 3. So here we're using the first shift theorem. So let's just remind ourselves what the first theorem is. Okay, so if the Fourier transform of some function equals f of omega, then the Fourier transform of the same function but multiplied by e to the jat is f of omega minus a. Okay, so that's the first shift theorem. So we're going to use that to answer these 2 questions. So first question is f of t equals 2 times u of t e to the 2j minus 3t. Okay. So let's just expand that and write it so that we've got the 2 exponentials. So we've got 2 u of t, we've got e to the 2jt and e to the minus 3t. Okay, so we'll expand that exponential. So we've got two exponentials. And then let's just write it in the form that we recognize it as. So I'm just going to swap the two exponentials around. Okay, now that it's written in that form, we can see that this part here looks like that's a function that's in the table. I'll call it g of t to make it different. And then we've got this part here, which looks like that. Okay, so we've got complex exponential multiplied by a function. So the Fourier transform of 2 u of t e to the minus 3t, we look that up from the table, is going to be 2 over 3 plus j omega. That's right. Yep. Okay. So that's f omega. So therefore, Fourier transform of e to the 2jt times 2 u of t e to the minus 3t, well, we can see that in this case, it will just be f of omega minus 2. Therefore, all we've got to do is just replace omega with omega minus 2 in the expression above. So that will be 2 over 3 plus j omega minus 2. Okay, that makes sense. Right, so let's move on to the second one, part B. So this one, we've got a function which is equal to 4 times e to the 3jt for t equal minus 2 to plus 2, and 0 elsewhere. So now we use the first shift theorem to find the Fourier transform of this function. Okay, so if we actually look at this function, we can see that it is obviously a rectangular pulse multiplied by a complex exponential. So we can say it's the same as, let's put the 4 outside as well. So it's the same as 4e to 3jt multiplied by this. So you can see in this case that this, obviously this part, we'll call that g of t. That's in the table, and it's multiplied by this exponential. So again, let's just go to the Fourier transform. So the Fourier transform of, let's put g of t, is equal to 2 sine 2 omega over omega. Okay, so that's equal to of omega. So in our case, Fourier transform of 4 times e to the 3jt times this rectangular pulse will be f of omega minus 3. That's right. Yeah, f over minus 3. And therefore, that's just going to be 2 sine 2 omega minus 3 over omega minus 3. Oh, so it's going to be 4. So don't forget the 4. So it's going to be 4 times that. Okay, so I'll let you write that down before we move on to the next. So the next question. Oh, question. So the question's just come in. Right. So this is about the exam. The exam is not a Canvas quiz. It's an actual exam paper in PDF format, which you have 24 hours to complete. Now, the exam timetable, I can't remember. I think it's at 9:30. So it starts at 9:30 on one day and finishes at 9:30 the next day, and that's the period of time you've got to complete it. So it doesn't start from, the clock doesn't start from when you start it. It starts at the 9:30 and ends at 9:30, 24 hours later. Okay, so it's not a Canvas quiz. It is an exam paper, but one that is open book, and you have 24 hours to do it. But it should only take you about 3 hours, really. Okay. And so, so therefore what you would do is you would upload your solutions to the Canvas link, and your solution would just be like as you would for an exam paper. Okay, so just submit your solutions, all the working, as a single PDF file. That's the important thing, because Canvas doesn't like multiple files, and it also makes our life difficult to mark as well. So I'm going to talk about this more in lecture, but there's many apps, but the one app that I use, Microsoft Lens, I think it's called, allows you to take a photo of your workings, and then you can sort of turn it into a single PDF file. So you just take a photo of each page, and it combines it into a single PDF file. That's what we recommend you use. Yeah, we'll talk about that afterwards in the next lecture. Right, question 4. Right, so this time we're using the first shift theorem to find the inverse Fourier transform of a function. So now we're given f of omega now, which is equal to 1 over omega plus 2j plus 1. Okay, so in this case, let's let g omega equal 1 over j omega plus 1, and then go to the Fourier transform table and see what that looks like. So we can see from the table we've got f of omega equals a over alpha plus j omega. Then inverse Fourier transform will have f of t is equal to a u of t, A of u of t times e minus alpha t. Okay, so obviously in our case, a equals 1 and alpha equals 1. So the inverse Fourier transform of 1 over, where are we? So 1 over j omega plus 1 is equal to u of t e to the minus t. Okay, so using the first shift theorem, so you can see this omega now is replaced with omega plus 2. So equivalently, we need to multiply u of t times e to minus t by e to the minus 2jt. So e to the minus 2jt times u of t e to the minus t. Okay, and that's because we replace omega with omega plus 2. So from the first shift theorem, that means you have to multiply the function in terms of time by e to minus 2jt. Okay, and I suppose you could also combine it into one function like that as well, if you wanted to. Okay. Part B. Okay, very similar again. We've got f of omega. Now we've got 2 sine 3 omega plus 4 all over omega plus 4. So again, we'll just let g of omega be 2 sine of 3 omega over omega. Okay, so just replace the omega plus 4 with omegas. And then from the table, two sine omega alpha over omega. The inverse Fourier transform of that is, of course, the rectangular pulse. So obviously, in this case, alpha equals 3. The inverse Fourier transform of 2 sine 3 omega over omega is going to be equal to 1 between t equals minus 3 and t equals plus 3 and 0 otherwise. Okay. And therefore, the inverse Fourier transform of 2 sine 3 omega plus 4 over omega plus 4 must be the same as the rectangular pulse, but multiplied by e t minus 4jt. Okay, or right. Okay, so two different applications of the first shift theorem. One to find Fourier transforms and one to find inverse Fourier transforms. Okay, now we've got a question 5, which is on the second shift theorem. So if we go to the lecture notes, so the second shift theorem, basically the Fourier transform of a shifted function is equal to e to minus j a omega times the Fourier transform of the unshifted function. So in this question, we've got if the Fourier transform of u of t times e to minus t is equal to 1 over 1 plus j omega, then what is the Fourier transform of u of t plus 2 times e to minus t plus 2? Okay, so quite straightforward. So here is f omega, the Fourier transform of the unshifted Fourier transform. And we can see here that a is equal to minus 2 because it's ut plus 2, so it's a minus minus 2. So t minus minus 2. So in this case, a equals minus 2. And then simply applying the second shift theorem, Fourier transform of u t plus 2 e to minus t plus 2 will be equal to e to the minus 2j omega times 1 over 1 plus j omega. Okay, so we multiply e to minus 2j omega by f of omega. Right, so I've got another question come in. Why don't we use the formula for the inverse? So I presume that means why don't we use the inverse Fourier transform equation? In that case, we don't, because we don't need to, basically. We can just use the table. So it's very rare that you actually use the inverse Fourier transform equation. Is that the question? Is I'm answering the right question? Okay. Okay. And another question's coming as well. have a look. Is the power in the exponential positive since the minus signs cancel each other? Assuming this is question 5 we're talking about, the power will be positive. Yes, you are absolutely right. Yeah. Well done. So yeah, so that's it's positive. Yeah, and because let me just highlight this. So here, so in that case, we had a equals -2. So it's going to be -2. So it's +2. Yeah. So well spotted. Thank you for that. Yeah. It says that in the solutions, but I just missed it. Okay. Right. So what I'm going to do now, I'm going to do question 6. And this is one where you have a function that isn't in the table. And we can't do anything. We can't use any other tricks. We can't shift any functions. We can't use time frequency duality. It's just a function that has been defined that isn't in any table. So in that case, we have to use the integral. I'm going to do one of these. I'm going to do the quicker one of the two. And in this case, you've got something which at first glance looks like the sigmoid function, but isn't, because it only exists between t equals -1 and +1. Okay, so the actual function is not a sigmoid function because it only exists, so it only has non-zero values between -1 and +1. So this, in this case, we have to use the integral. So thankfully, they're just two constants, -1 and +1. So we haven't got to do anything that involves inching by parts. So what we do, we split this up into two integrals. We first of all got one integral from -1 to 0, and that's -1 times e to minus j omega t dt. And then another integral from 0 to 1, which is +1 times e to minus j omega t dt. So two very simple integrals. So in this case, integrate the first one. So it'll be e to minus j omega t over j omega. So these minus signs will cancel out. That's between 0 and -1. And we also have e to minus j omega over j omega. Between 1 and 0. So putting the values of t into each one. So if we first of all got e to the 0 over j omega minus e to the minus j omega over j omega. So that's the first one. Plus minus e, missing there, minus e to the minus j omega over j omega, and then minus e to the 0 over j omega. Okay. I'll just collect everything we've got. Okay, and so we can see we've got 2 over j omega minus 2e minus j omega over j omega. Now, something's not quite right somewhere. I've just spotted it. So first, so on this row here, that should be a plus. I just realised, yeah, it should be a plus. So this is right. It should be a plus because t equals -1. Put it into there. It will make that exponential power positive. Okay. So it's e to the plus j omega. So, right, and in that case, what happens is we have minus e to the plus j omega over j omega. Minus e to minus j omega over j omega. And now we can see that this term here looks very much like a sine, because if we use Euler's equation for sine wave, that is e to the j omega minus e to minus j omega, so sine omega. Okay, so we can see that it looks very similar to that. So what we've got is 2 over j omega minus all of this and we can replace that with, oh, hang on, sorry, made a mistake. Yeah, not that. So it should be cos because I've jumped the gun a bit. So hang on, forget that. What I want, this part here, sorry, I've underlined the wrong bit. That is the same as cos. Well, there's a cos of omega in there. Okay, so you can see that we can actually replace that exponential terms with 2 cos omega over j omega. Okay, because basically what I've done, I've multiplied both sides by 2. We can see that the numerator is the same as 2 cos omega. So 2 cos omega divided by j omega. Okay. Which of course we can simplify for that. Okay, so I mean that's a question, just a possible question, something like that could come up, where you'd have to show the working like this. So that's a function that isn't in the table, and there's no other way of finding it unless we do the integration. Okay, so please do ask any questions if you've got them. Oh, what time is it? So let's just do question 8. We'll just do one time frequency duality question. So basically, we want to find the Fourier transform of Fourier transform of 1 over 1 plus jt. Okay, so that is a function again that isn't in the Fourier transform table, but we can use time frequency duality because from the table, we've got 1 over 1 plus j omega. And the inverse Fourier transform of that is from the top row of the Fourier transform table would be u of t e to the minus t. Okay, so that we've got that from the table. So we have to remember, so this here is f of omega, and this one here is f of t. So the time frequency duality principle is Fourier transform of capital F of t is equal to 2 pi times lowercase f function minus omega. Okay. So in this case, we've got the Fourier transform 1 over 1 plus jt. That's our f of t. And as you can see, we've just replaced omega with t. That's equal to 2 pi times f of minus omega. So that's 2 pi u of minus omega e to the minus omega. So I'm going to put all the signs in so you can see where this comes from. Right. So in this case, we've got 2 pi u of minus omega e to the omega. Now, when we have a delta function, we've said the delta function is even, so delta of minus omega is plus omega, but the step function isn't even because it doesn't reflect in the y-axis. Yeah. So when you have a step function, it looks like this. So that's u of omega, okay, and therefore u of minus omega would look like this. So we have to stay with u of minus omega. We can't simplify it to u of omega because it's a different function. Okay, so this is the final answer on that one. Actually, I tell a lie. Is that right? Yeah, I think it is. Yes, I think that's fine. Okay. Right. So, okay. So therefore, that's the final answer, and we can't simplify that anymore. Right. Okay. So the question come in. So we know we asked to derive a transform that we could glean from the table. I think the word glean. Yes, you could. If the question says prove that the Fourier transform of something equals something, then you would have to prove it mathematically. Yeah. But only if the question specifically asks you to do that. Okay. If it doesn't, you just use a table. But you know, I could ask you to prove the Fourier transform of something that's on the table. Yeah. Okay. Right. So what I'll do, just finish off with one last question, and that's question 10. In the previous question, I think there's an extra 2. Where in front of the code? Previous question. Forgot what the question was now. I don't think there is an extra 2 in front of the cosine. In the previous question, I think there's an extra 2 in front of the cosine. Oh, yeah. Well spotted. Sorry, yeah. Yeah, so obviously, if you going from here to here, yeah, of course. No, we don't need that. Yeah, well spotted. Yeah. Right. Okay, so thank you for that. So go back to question 10. For question 10, we're given a transfer function for an LR circuit. R over J omega L plus R. Determine its impulse response. Right, so this is the same as saying V out of omega divided by V in of omega. Okay, so therefore V out of omega is equal to V in of omega times R over J omega L plus R. So the impulse response so that means that V in of T is equal to a delta function. That's what the impulse response is. So therefore, V in of omega will be equal to 1 because the Fourier transform of a delta function is 1. And V out will then be simply R over J omega L plus R. Okay, because we're multiplying that by 1. So this is just like the Laplace transform question. You've got to make the function look like something in the table. In our case, what we can do is, first of all, divide top and bottom by L. And if we do that, then it looks like a function that's in the Fourier transform table. In fact, it looks like this one. Yeah, so from the table. And we know that the inverse Fourier transform of that is the pulse. Sorry, it's the decaying exponential. So that we know that from the table. And then, so therefore, in this case, A is equal to R over L, and alpha is also equal to R over L. So therefore, V out of T is going to be R over L times U of T to minus R over L T. Okay, so there's substituting values directly into here. That's what we get. Okay, so I think that's a good place to end the tutorial. Are there any questions that you'd like to ask me while I'm here? Or otherwise, we can wait till tomorrow. So, okay, in that case, I will let you all go and see you tomorrow at 11 o'clock. Okay, thanks very much. See you later. Bye.